Can everyone hear me? Thumbs up? All right, okay. So I'll be talking about demonstration of non-stochastic Hamiltonian in coupled superconducting flux qubits. I start with non-what, but I'm pretty sure you're not questioning that right now because of all the non-stochastic talks, but still I'll go with my slides. A k-local Hamiltonian, H is stochastic, if there exists a local basis such that it can be written as a combination of real symmetric matrices having all non-positive off-diagonal elements. So here, I will highlight in red if there exists, because that means that seemingly non-stochastic Hamiltonians can sometimes be transformed into stochastic Hamiltonians via a set of local transformations. However, finding such set of transformations is hard on its own. All right, so why do we care about non-stochasticity? It has the potential to enhance the efficiency of quantum annealing, I guess by a little bit, and as the size grows, not as much, according to Itai. It's useful in describing equilibrium properties of quantum systems. And finally, algorithms like quantum Monte Carlo suffer from the sign problem in simulation of non-stochastic Hamiltonians. So let's start with something that we're familiar with, the transverse field Ising model with 2 qubits. I'll first start with a single qubit, which you might find in a DWave quantum annealer. Here, I'm showing the energy landscape of a single qubit. What we're doing is we're encoding the logical basis perpendicular to the energy eigenbasis. That means that up and down states correspond to 2 wells of this energy landscape. For a 2-qubit Hamiltonian, this energy landscape will be just a 2-dimensional version of that. So here I have 4 valleys encoding up, 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 down, 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 up states. And in a transverse field Ising model, there's only single qubit tunneling terms. So that means that to go from an up-up state to a down-down state, I have to have 2 qubit events. I have to go from up-up to up-down, and then from up-down to down-down. So let's look at the terms in this Hamiltonian. All right, so first of all, let's get the lingo straight, since everyone is throwing around a bunch of words and terms. Well, I want to make sure that it's clear. So what we do, we call this CJJ bias, which is the flux bias applied to the CJJ loop. And this bias controls delta. So this is the barrier, energy barrier of the qubit. Second, we have the flux bias applied to the qubit body. And this term controls the tilt of this energy landscape. So that controls the strength of this H. And finally, we have a flux bias applied to the coupler, which controls the strength of this coupling between those 2 qubits. And this is an inductive coupling here. All right, so I guess we all know that this is a stochastic Hamiltonian, which means that we need more terms. So I would like to pause here. Normally, I had a Bob Ross image. And then IP came to me and said, you cannot use that Bob Ross image. So I was on a plane, and I drew this Bob Ross image in Paint. So what we do, the first step towards a non-stochastic Hamiltonian, we just put a little capacitor in there. So this is my little capacitor. It's a fixed capacitor connecting these 2 qubits, and it's contributing a charge-charge coupling, which we expect to have turn into a YY coupling in this Hamiltonian. So what this enables is a direct path between up-up and down-down states. Instead of having to go through single qubit path, I can go directly from up-up to down-down, for example. Okay, so now that we have our circuit, we first have to extract the circuit parameters that we really just fabricated. The reason why we have to do this is because the fabrication process, there might be differences, things that are happening in the fabrication, and there might be things that we didn't account for. So in order to do that, we first start with a single qubit spectroscopy. What that means is that I'm keeping the second qubit in a monostable state, so it looks like this, the energy levels. That means that it doesn't affect the qubit that we're measuring as much. And then what we do is we just set the CJJ bias, so this is the delta of the qubit, to a given value. And this gives the energy gap between the ground state and the first excited state. And now we apply a microwave signal at a given frequency. If that frequency matches this gap, then in the readout, I will not always see the ground state, but now I will be populating the excited state. So in this figure here, that's exactly what we do. In the x-axis, I'm sweeping this gap between the ground and the excited state. And here, the y-axis gives the frequency of the microwave signal. As soon as this gap and the energy of the microwave signal matches, I see a change in population of my ground state. So that means that I can extract a delta from this measurement. We also do 2-qubit spectroscopy in order to extract these circuit parameters. And what this means is that instead of keeping the second qubit at its monostable state, now we're letting it interact with the first qubit. So in these experiments, what we did is we set the inductive coupling to 0, so there's no ZZ term. That means that I'm working with a Hamiltonian like this. So the only coupling will be coming from this YY term. If there was no YY term, I would see exactly the same figure that I showed in the slide before for a single qubit, since I'm only applying the microwave signal to the first qubit. I'm not applying a microwave signal to both, it's only applied to one of them. However, what we see is anti-crossing. And this anti-crossing is related to this YY coupling strength. So here in these three figures, what I have is second qubit at 1.5 gigahertz, at 2 gigahertz, and 3 gigahertz. So this is the gap of the second qubit. That means that as I tune the delta of the first qubit, that number shouldn't change at all. And this line here would have corresponded to these 1.5, 2, and 3 gigahertz lines, would correspond to the second qubit, only if they were not coupled. But because they're coupled, I see that instead of seeing the single line of delta measurement, I see an anti-crossing between these lines. And this anti-crossing depends on the strength of the delta of the second qubit, because it goes with this delta term. Its strength depends on the delta term. So this is a driver. All right, so taking these experiments, the 2-qubit spectroscopy and the single-qubit spectroscopy, we can fit to a squid model and extract all of the circuit parameters. And they're basically within what we expected, what we designed them to be. So now that I have this model and I have my parameters, the next question to ask is, what happens when I'm not fitting for parameters and I'm doing different experiments? So since I'm interested in non-stochastic Hamiltonians, I would like to test this on a non-stochastic Hamiltonian. At h equals 0, this Hamiltonian has both positive and negative off-diagonal elements in the computational basis that it's written in, right? So it looks like it's non-stochastic, but there is a local transformation that will make it stochastic. So non-stochasticity with this Hamiltonian is only achieved at non-zero h. That means I want to look at theory versus experiment at non-zero h without any fitting parameters. So here I'm changing the delta of the second qubit. I'm looking at changing also the energy of the microwave signal that I'm applying when there's an H bias applied to both of these qubits. And I see that in the background is my experiment, and there's actually a white line on top of that. That's the theory calculation, which is right on top. I can do the same thing, this time sweeping the tilt of the second qubit while keeping the tilt on the first qubit constant at a given inductive coupling. Here again, the white lines are right on top of the experiment. And finally, I can do the same thing for non-zero delta and h on both qubits while sweeping the inductive coupling. Here, again, I have the white line on top of the experiment, and the dashed line shows what would have happened if there was no linear bias applied to these qubits. So I see that these two lines are crossing here when both h's are 0, And when there's a non-zero H, there's an anti-crossing at that point. Okay, now that I have a squid model, I'm really interested in qubits, because that's the business here, right? So normally, what we do is we take a squid, we scratch out the higher energy levels, and we say that, okay, good, we have a qubit now. And this kind of works in most cases. And now the question here is, how legitimate is this to do this approximation in the context of a capacitive coupling in there, just a fixed capacitor? So it turns out that, yes, you can find a qubit model that you can simplify the squid model to. However, you have to include the effects of higher energy levels. And we can see that by this appearance of this XX term. This XX term is here because of the interaction of the two lowest lying levels of the qubits with their higher energy levels. So the answer is, yes, there's a qubit model, but it's more complicated than what we're used to. In addition, this spectra shows, so these lines represent the qubit model for this experiment. So this is the ZZ coupling, the inductive coupling, which we, as expected, goes from -1 to 1, since that's what we're sweeping here. The capacitive coupling is constant, so this YY term is constant here. And then this is this XX term that's appearing from the higher energy levels. This Hamiltonian is non-stochastic in this white region and becomes stochastic beyond that region. So there's a transformation that can turn it into a stochastic Hamiltonian. All right, now that we have our qubit model and I have my system, I wanted to do some experiments, right? Let's have fun. So we did some coherent oscillations. What does coherent oscillations mean? We initialize the qubit in one while, and then reduce the tunneling barrier, and let the qubit oscillate between those two states, up and down states. And the reason why this happens is because in its ground state, it's in a superposition of up and down states. And if I prepare it in its down state, it's going to tunnel through this barrier and oscillate between those two possible states. I can do this for a single qubit and a two-qubit version. So for a single qubit, here what I'm showing is preparing the qubit in an up state and measuring the coherent oscillations of this qubit between up and down state for both of my qubits. So the red and blue show two different qubits here. The qubit gap here is 1.5 gigahertz, and within 5 nanoseconds, I'm seeing 7.5 peaks, which is exactly what I expect from a coherent oscillation. So for two-qubit coherent oscillations, I can do the same thing where I prepare my qubit, I prepare my qubit in its up-up state, and there's a ferromagnetic coupling between those two qubits, so the preferred states are the up-up and the down-down states. And what we see is oscillations between the up-up and the down-down states here. And we don't see much contribution from the down-up and an up-down states. This was a single line that's cut out from this spectrum. And I can repeat this experiment for a wide range of inductive couplings. So what I expect is, since I'm preparing this system in an up-up state, that means that in a ferromagnetically coupled section of this experiment, I will be preparing my system here. So this feature that I'm seeing corresponds to this two dashed lines crossing. It's the cancellation of the single tunneling events with this YY, with the tunneling mediated by this YY term. All right, so how does this compare with theory? Here I'm showing the experiment and the simulations. These simulations are done using the qubit model, not the squid model, but the reduced qubit model. And we see that there's a really good agreement between the two. We can repeat this experiment by preparing the state system in an up-down state and measuring the down-up probability population. Here, the feature that we're seeing here corresponds to the crossing of these two lines. And finally, since we're interested in non-stochasticity, we can repeat the same experiment when there is a tilt applied on both of these qubits. And we see that again, simulation and experiment agree at this feature point. All right, so in summary, we demonstrated 2 qubits coupled by 2 conjugate degrees of freedom. We showed that we can achieve YY and XX coupling, although accidental. And this is the first time that we realized a non-stochastic Hamiltonian in a quantum annealer. All right, thank you so much.
Oh, you know, I promised that I ask you this. So the circuit Hamiltonian is stochastic.
Yes.
Right.
Yes.
Why can't I simulate it and get basically results, all the results that you got with numerical simulations? I don't have to, you know, add talks about qubits and qubit interpretation. I'll just go to the circuit. This is what DWave does, the circuit. I'll simulate the circuit, and I'm done. So what's wrong with this?
Yeah, okay, so thank you so much. So the question is, the parent Hamiltonian is stochastic, and why can't I just use that? And the answer is yes, the parent Hamiltonian is stochastic, but it's written in a big flux basis. So I don't have a 2-level system now, I have a many-level system. For 2 qubits, I showed it, the theory is right there, it's really easy to do, but as you scale the number of qubits, at some point it becomes really, really hard.
Okay, I'll just a comment that people, I think, can do, you know, continuous variable quantum Monte Carlo. So I believe, we're actually doing it right now, that you can indeed simulate efficiently or with quantum Monte Carlo the Hamiltonian. But I don't have answers, but...
Yeah, so I definitely want to see it.
Yes,
and I'm sure you will email me once you have that.
My understanding is that the YY terms are driven with the X term. They're not part of the problem Hamiltonian. The problem Hamiltonian is still just Z's.
Yeah, exactly. Yeah.
Is it possible to get the YY term into the problem Hamiltonian?
So it becomes a different question when you have quantum annealing, but at the same time these YY terms. So at this point, what you would do, I guess, is to have a tunable coupling, for example, a capacitive coupling, and then measure mid-anneal. And at that point, you'd have the YY term, you'd have the ZZ term, right?
Well, that YY term is time-dependent, and it has the same time dependence as the X term.
Yeah.
And so for universal quantum computing, if I have ZZ plus YY in the problem Hamiltonian, I can find the ground state of that in a certain amount of time, which is comparable. I mean, ultimately, I want to be able to find the ground state of problem Hamiltonians that have ZZ plus YY.
Yeah.
And the driver is not the most important. I mean, for universal quantum computation, I don't need the driver.
Yeah, I totally agree. Yeah, but in this case, the way it's applied, it contributes to the driver term.
Okay, is there any way to get it into the problem Hamiltonian?
I don't know.
Okay, thank you.
Hi. So you called the coupling capacitor little, but it looks like the capacitance.
I can't hear you. Sorry, I can't hear you.
The coupling capacitance seems to be larger than the qubit self-capacitance. So when you said it was small, did you mean it's physically small because it's a different geometry, or?
So can you repeat that again?
In what sense is the coupling capacitor small?
Did I say that?
Yes.
Oh, I just said it's a reference to Bob Ross. Let's put a little capacitor in there.
And one more question. Your spectroscopy data looks very clean. Did you have any problems with background modes, or you have to do anything to get rid of them?
I didn't do anything. This is raw spectroscopy data.
Cool.
Yeah.
Thanks.
So, two-part question. First, the time scale for these coherent oscillations, what is it?
Time scale for the coherent oscillations?
Yes.
So here, what I'm showing are in nanosecond scale, right? Yeah, so this is time axis. This is going from 0 to 10 nanoseconds.
Okay, so one could argue that these are not coherent oscillations because they're oscillations between computational basis states, and you haven't actually demonstrated superpositions. And actually, on this time scale, I would expect that, well, nanoseconds, maybe the system is still coherent. It's plausible.
So this is still within our T1 and T2 times.
Uh-huh.
Yeah.
So, okay, so that's good. But do you have actual evidence that these are coherent oscillations as opposed to just like classical oscillator oscillations between populations? In other words, do you have a way to demonstrate that you have created superpositions here?
We can do Ramsey spectroscopy in addition to these coherent oscillations to show that it is actually coherent, quantum coherent.
You can or you have?
You can. We haven't. We don't have it in the fridge right now, but eventually we're planning on doing it once we have it in the fridge. Yeah.